Hello, everyone. And sorry I couldn't all see each other in person this summer, but I am glad we get to exchange some ideas this way remotely. So today I want to talk about a paper I've been working on for a couple of years. It's called Experimenting in Equilibrium. It's joint with a colleague of mine, Kwang Shu, in my group here. This is maybe a more applied project that many that have been covered at this workshop this year, but at least I thought maybe some of you would be interested, just because first, it's an application area that hasn't gotten that much attention in statistics, so at least I enjoyed thinking about it. And second, it kind of connects different themes that usually don't come together that much, kind of around experimental design on the one hand and online learning, and gradient descent type learning on the other. So I think that this might be a connection where kind of here we're really just scratching the surface, and there might be a lot more to say around kind of how do you design experiments to drive gradient descent style learning methods. But so anyways, this talk, I mean, in its application context, I guess it's somewhat set into problems that come up quite often in Silicon Valley. By now, you have a lot of different companies around here that had realized that they can run randomized trials in a bunch of different contexts, and it's useful. I think in the past, randomized trials have always been very common in places like pharmaceutical companies, where, of course, if you're testing a drug, then it's very important to run rigorous randomized trials to test what works and what doesn't. But nowadays, at least around here, they test everything. Right? If you want to change a font on a message, they're going to run a randomized trial and see which one gets more engagement. And this works very well in many situations. But what's been interesting is kind of as interest moves towards more kind of ambitious statistical problems, suddenly running randomized experiments gets more complicated. And one setting where that comes up all the time is that when you have, if you imagine you have a platform that's kind of running a miniature economy, people can buy and sell things on it, and you have supply and demand have to match. Then running a randomized trial is more difficult because, say, if you kind of reduce prices for one set of people, they might buy more things, but so then things would be out of stock for others. So kind of this idea that if you only give an experimental intervention to one person, it only affects that person and not others, that breaks, because anytime you intervene on anyone, you get some system-wide effects. So this makes experimental design a lot harder. What is the issue here? And the issue, kind of at a very high level, it's just interference, which, at least in the causal inference community, is very well known. I think the most famous example of interference is in studying the effect of a vaccine. So I guess this wasn't quite as timely when I made the slide, but yeah. So on this slide, imagine, for understanding the effectiveness of a vaccine, there are two things that matter. There's, did you get vaccinated, and what fraction of other people in your community got vaccinated. So let's say we're looking at the coronavirus now, and currently there are no vaccines, so we're here. None of us are vaccinated, and the fraction of the population vaccinated are both, is 0. And now let's say someone actually propose a vaccine, and it's not a perfect vaccine, so it doesn't give you full immunity, but it still helps some. And let's say they ran a randomized trial seeing what is the protective effect of this vaccine. So now we're going to move you from not being vaccinated to being vaccinated, but it's still a pilot study, so most of the population is still unvaccinated. And what this randomized trial is going to measure, this is going to measure the effect of you being vaccinated in a world where most people are not vaccinated, this is going to be something. But actually, the thing that's policy relevant is asking what would happen if we went from having no one vaccinated to everyone vaccinated. That is, from going from this state to this state. And this is actually a much bigger effect for well understood reasons, right? Herd immunity. If a large fraction of the population is vaccinated, then it's harder for the disease to progress, and that gives you a protective effect that's beyond the direct effect of just you being vaccinated yourself. The point is just, if you ran a simple randomized trial for the effect of vaccination on a small subset of the population, you wouldn't capture these network effects, these herd immunity effects. So you would be wrong about what would be the value of deploying a vaccine to everyone. You would underestimate its benefit. And this is kind of one problem in interference. So in the causal inference literature, we typically refer to this as interference. There's some work on it that I'll say a few more words about soon. But kind of, this is quite general. And one might feel like if any approach to working with interference that can deal with any type of interference you'd ever see in practice kind of is too general and might not have much power in any kind of specific application we care about. And so as one application of this type to kind of get us thinking and have a kind of concrete example to support and kind of our intuition is, suppose there's a sharing economy platform, and so there's demand coming in for some tasks to be performed. There's some freelance workers, and then the platform tries to recruit freelance workers to satisfy this demand. And the way this is going to go is that there's a loop where every day the platform first kind of publishes a payment PI. It's willing to pay workers for each unit of demand served. Then the workers, they see PI. Based on that, they choose to become active or not. And then, so some fraction of all workers who could have potentially chosen to become active on the platform that day, in fact, become active. And then kind of, once you have a specific number of workers and a specific amount of demand, the demand is randomly allocated among everyone who's active and is not already busy. And you could think of this as a toy model of how something like TaskRabbit works, or how ride sharing works, and so forth. And so anyways, I think just by inspection, one should see that kind of this as any kind of equilibrium model. Here, different agents have different kind of preferences. The workers would generally prefer to receive large payments and have few other active workers, so they don't need to compete for the available demand. On the other hand, the platform would want to have low payments and many active workers to make sure all the demand gets served. And kind of, if this is the general equilibrium context, we're going to think about how can you learn good kind of parameters for this marketplace, where here the kind of free parameter is the payment scheme. So you want to kind of make sure that tune payments that kind of both balance the platform's revenue, but also like that enough people are willing to join the platform, so all the demand gets served. So anyways, the question is how should one choose this PI here? And here we get to the statistical question, which is the first thing one could try to do is the slightly naive thing. You want to know how people respond to different payments. So just kind of take a small slice of traffic, randomly assign them different payments, and see how they respond to this. But this kind of clearly won't work, right? if you take a small group of people and pay them more, I guess in this case, this group might respond very strongly to that boost in payment. But if you take a big group of people and pay them more, then at first everyone might respond strongly, but now more people are going to join the marketplace. So this means that actually that the ratio of supply to demand is going to go up, and then you're going to have excess supply. So actually, when you randomly allocate demand, a lot of workers are going to end up working less. So it's actually going to kind of a big boost in payments is going to be less desirable if you give it to everyone than just a handful of people. So kind of and a randomized controlled trial won't let one reason about that. So this is the difficulty, and kind of people who think about these problems are well aware of this. So what they end up doing instead is they run randomized trials on non-interfering groups. So this would be kind of, let's say you have one marketplace in San Francisco, one in Seattle, and one in Chicago, and one in Boston. Then they'd assume that these marketplaces don't interfere with each other. So you'd set one set of conditions in San Francisco, another in Seattle. And this is fine. This properly deals with interference. But this is at a huge cost in statistical power. Because essentially, if you had a bunch of people in your marketplace, millions of people, you might feel like for any experiment you run, your sample size should be millions. But if you only have 20 cities and you're randomizing across 20 cities, well, then your sample size is 20. And kind of any kind of macro level perturbation in each city can completely break inference here, or kind of cause a lot of noise. So that's also a difficulty. And here, so in this context, the question of this talk is, can we do a little bit better and kind of use our understanding of where this interference is coming from? It's not that workers just generically interfere with each other. It's like worker A interferes with worker B if worker A does more work and therefore reduces the expected amount of work worker B can do. That's kind of the only way interference can arise. And it seems like we should be able to capture that and understand that and correct for that. So here we're going to try to do some mean field modeling for that. Okay, but just before going there, I promised a few words about how we usually do interference in the causal inference literature. And it's just a very different approach. This is maybe easiest to think of, what people do now is maybe easiest to think about in terms of a social network or other kind of network. You have people are on a graph. There's like an edge between two people on a graph if they're friends. And then what is interference? We were saying that if A and B are friends, then if I kind of intervene on unit A, this might also affect unit B. If you intervene on my friend, maybe my friend will tell me, and it'll also affect me. So these kind of interference could occur in clusters. They could occur along a graph or another structure. And then there's a fairly large amount of literature that kind of does things like, how can you adapt Fisher's permutation test to test various null hypotheses under an assumption where you have interference along a graph that is intervening on any node on a graph might not just affect the node, but also its neighbors. So this is very relevant in some settings. It's kind of, this kind of classical approach doesn't talk about why interference happens. It just recognizes that interference occurs along a graph and tries to be robust to that. Here we're in a different world. On the one hand, kind of it's probably no surprise that these methods to work essentially require the exposure graph to be sparse. That is the kind of the neighborhood graph if you're thinking about a social network. In our setting, obviously the graph is not sparse. Any worker can interfere with any other worker just by kind of because everyone's
competing for the same demand pool. So this kind of exposure graph-based approach just doesn't work. But on the other hand, we're willing to model interference. We have an idea where it comes from. So we just need to take a different approach. And kind of what just to be more specific about what I mean by modeling, is essentially the core assumption we're going to make here, I think as I've hinted already, is that it's a marketplace. What drivers care about here, say, or kind of workers, sorry, but driver there. I've often talked about this in the context of ride sharing, which is kind of a good motivating example. At least for me, it's an easier motivating example because it's a problem space that many of us have personal experience with. But so, anyways, the interference is mediated by the assumption that each worker responds to expected revenue. So, and the implication of this is that if the platform offers a given worker a given payment per unit of demand served, then what that worker is going to consider is essentially the amount of demand they expect to kind of be available that day, the number of other workers who are going to be active that day, and then these two numbers kind of induce a belief on the expected amount of demand they're going to get to serve. And then they care about essentially the product of how much you're paying them per unit of demand and how much demand they expect to be able to serve in that day. The point here is that if interference occurs, it's all kind of mediated by total supply. It's all mediated by the total supply because total supply modulates the probability of being able to serve a unit of demand given that you join the marketplace. So this gives us a lot of structure we can work with. I should also note that this is, of course, it's a strong assumption, but at least in the ride-sharing context, which is a leading example for applications of this type, it seems to be reasonably well aligned with empirical evidence. So, okay. So to go into kind of a little more details, here's kind of a model to get started with. What happens is that every day the platform chooses the distribution pi and then promises a payment pi to each worker for per unit of demand served. And if a fraction mu of so there's always going to be a pool of potentially active workers. If a fraction mu of workers is actually active, then the expected amount of demand any given worker gets to serve is q of mu. This function q is going to play a key role in the analysis. And then workers have a random outside option bi, such that given the distribution pi, the ith worker is active with probability fbi, and this fbi is some function that essentially takes pi, how much you're paid per unit of demand, times q of mu of pi, that is how much demand you expect to be able to serve given the fraction of workers mu determined by the distribution pi, and you're going to compare this to some outside option, and that's how you're going to choose to become active or not. Here we put a logit form just kind of for concreteness, but actually you don't need this. Any function f, any random function f that's kind of monotone increasing and smooth is fine. And then kind of the point is that once you get the formal results, I'm going to check that this equilibrium is in fact unique. So the system is going to be in equilibrium, meaning that mu of pi is actually the expected activation probability. So this captures the system, and the goal, again, remember, is we're going to the goal here, I'm allowing for personalized payments, but in some sense, the goal is for the platform to choose a target payment P that's optimal for some utility criteria. And how are we going to learn about what's a good criterion P? It turns out, and I'm going to get to this more soon, in order to figure out how to learn a good P, you essentially need to understand, or you can always think that this pi is essentially going to be concentrated at a target payment P. You need to understand things like d mu dp. How does the total fraction of workers active change if you change payments? It turns out the most notions of utility that you care about, if you can figure that out, then you can figure out the derivative of the utility with respect to changing P, and then you can optimize the system. So the question is, how do we get d mu dp? And here it's going to take a little bit more work. So, okay, not surprisingly, we're going to need to run some kind of experiment to identify this. And a first experiment that might come to mind is, let's take our target payment level P and perturb it by plus or minus zeta. So pay everyone just a little more or just a little less than this target level P. And what's interesting about this is if we kind of assume that everyone's kind of distribution of outside option or kind of is continuous, or that activation function is continuous, then and smooth, then adding these small mean zero perturbations to the target payment P shouldn't affect total supply, because you're kind of not changing the average participation decision. So this doesn't lead to any interference in itself, and it's going to let us measure something. The something it's going to let us measure is, sorry, if we write zi for the choice of the ith worker being active. And so then what we're going to do is we're going to regress zi, the choice of being active, on epsilon I, this exogenous shock to the payments. Then this is going to recover a marginal response to delta that ends up being interesting. So just a few words about this marginal response. First, it's not policy relevant directly. So what we care about is d mu dp. That is, how does the average participation rate in the market change if you increase payments for everyone? Delta is not an answer to that question. What delta answers is, if we keep the system in equilibrium and we pick one random person and we pay them a little bit more, how much can we induce? How much more likely are they to join the marketplace? But it turns out that kind of you can do some kind of mean field modeling to go from delta, this thing that's easy to measure, to d mu dp, the thing you actually care about for optimizing the system. So that's kind of at a high level. I should also note that if any of you kind of have background in econometrics, this might feel a lot like instrumental variables regression, and it really is, right? If you look, what is this OLS? Think of epsilon as a perfect randomized instrument for kind of shocking PI. Then this linear regression of ZI, that marketplace participation on epsilon I, is the reduced form regression, and this 1 over zeta we're dividing by here is just the first stage, right? It's the effect of epsilon on PI. It's just we already knew the first stage a priori. So you can really think of this as similarly to how you think about two-stage least squares, and therefore delta is like the local average treatment effect from kind of a small shock to a continuous treatment. So if you spend a lot of time thinking about those kinds of quantities, maybe that gives some intuition. Similarly, if you've thought about the interference literature a lot, this is very closely related to what's often called the direct effect in that literature, because it kind of measures how much, if I change your payment, how does that affect your marketplace participation? And then there's also the indirect effect. If I pay everyone else more, how does that affect your marketplace participation? Okay, this is just to get ourselves oriented. The learning approach I'm going to talk about soon is kind of really centered around what can you do once you've run this experiment and recovered this delta hat. But before getting there, I just want to quickly verify that this actually works empirically. So here is kind of just a simple simulation study. We have data across 200 days. Each day is separate. So you could imagine you have a marketplace. In the morning, everyone kind of chooses whether they participate or not. Something happens, the market clears, everyone goes to bed. Next day, new day, the system repeats, except just days are different from each other. Some days are sunny, some days are rainy, and that creates some noise, and you want to be robust to that noise. And what are we going to want to do? We're going to want to use a payment P that maximizes some utility function U of P. And how could we think about doing this? Well, there's the kind of global experimentation. This is kind of the normal thing to do. This is that corresponds to what people actually do out there, which is find non-interfering units and experiment across them separately. So you could find different cities, experiment across them separately. Here we have consecutive time periods that are non-interfering, so experiment across them. This is, if you're from the kind of bandit literature community, this is kind of very closely related to zeroth order optimization, because kind of what you're going to do is every day you get to pick some target price PT, deploy it for everyone, observe a realized utility, and then try something else. And every day you can try something and kind of in the end pick PT that gives you kind of a high average reward. And then, so this is kind of, a lot of baselines fall roughly in this category. And then the second thing I'm going to talk about is this one, that is run these micro perturbations on P, estimate a marginal response function, map it to utility derivative via equilibrium modeling, and then estimate, and then update the system by gradient descent. And there are, so here, it's just an empirical comparison. So there are two numbers that matter for a learning algorithm. So I ran the algorithm for 200 time periods. So there was the kind of average daily regret during the experiment. And another thing you might care about is the future expected regret. That is kind of at the end of 200 days, I picked some target P, and let's say I just deploy that from now until the end of time. How well do I do with that? And you see there's just an order of magnitude difference between, this is our local experimentation scheme where we run these micro perturbations and learn with that. We kind of, to the accuracy, like in order to fit a scale where we fit the error of the global experimentation, this kind of seems to have zero error. And this is not an accident. In the theory, we're going to show a separation in rates of convergence between the two methods. So this kind of backs this result. Here for the global experimentation, I tried a lot of things. The thing I could get to work the best was actually kind of a simple explore then exploit. So for the first T0 time period is you randomly explore, and then from T0 to capital T, you exploit, and all these dots correspond to different choice of T0, kind of different choice of how long do you explore before you exploit. And kind of regardless of how you tune it, you just have way more error than this method. And here you just see a sample path of learning. This method does learn quite fast. That's why we get low regret. Okay. So now to actually say something about this. So I need to make one more thing that I had kind of glossed over before. I said that days are different. Some days are sunny, some days are rainy.
this kind of, so you kind of have marketplace level demand fluctuations. Accounting for these is important because they occur in practice, and if you don't have these, you're going to think that things that don't work work. So we're going to assume that there is a daily state variable A, such that A can kind of change everything. It can change the distribution of demand. It can change the distribution of worker outside options. But kind of once you condition on A, then we're going to be in a large marketplace and everything concentrates. In particular, the distribution of demand concentrates conditionally. The second is we're going to think that there are some marketplace dynamics that kind of govern if there's some amount of demand and some amount of supply, how many supply-demand pairs can you actually create? Well, maybe not everyone can be matched with everyone, because if two people are too far, maybe they can't get matched. Any concern like this always comes up in a real marketplace. And here our assumption is just that the platform understands this, and that the process is scale invariant. That is, if you double the demand, you double the supply, the fraction of matches you get remains constant. And this function omega is the thing that governs this matching rate. One could certainly do asymptotics differently. Like, I think if you imagine that you're doing ride sharing and your model is that you just have more and more people in a fixed size space, it's kind of the end of a sporting event, and kind of at some point you're just going to have a huge amount of demand, a huge amount of supply, and everything gets matched perfectly, then this wouldn't be a good assumption. But if you think the way that asymptotics grow is that you have a city and the city is just getting bigger and bigger, but still you can only match people in a given neighborhood, and kind of locally the density of supply and demand doesn't go up, then this kind of scale invariance might be a reasonable assumption. So we're going to do this. And then from a modeling perspective, like I said, there's this daily state I need to put in the model. And we're just going to write down the model conditionally on A. And conditionally on A, everything happens just the way I said. Okay, now I should actually tell you something about this. So first, in this model, there's a unique equilibrium. In this equilibrium, the number of active workers is a binomial distribution. That's not so surprising. Fact number two, again, not so surprising, but very important for the purpose of our analysis. As the marketplace size gets large, the equilibrium and its relevant derivatives converge to a mean field limit. And everything I'm going to say from here on out is actually going to be about the mean field limit. And here's kind of a first interesting thing. So remember, I said everything, all our inference is going to be driven by these kind of micro perturbations to the payment scheme. So essentially, instead of paying everyone $15 per unit of demand served, we're randomly going to pay some people $15.10 and others $14.90. And then we're going to kind of look at is like paying people plus 10 or minus 10 cents. Is this going to change their marketplace participation decisions? And if we run this experiment and then regress marketplace participation on these exogenous shocks, then as long as the size of these shocks goes to 0, but not too fast, you can check that this marginal response function converges to, or kind of this delta hat converges to the marginal response function, which has the following form. So again, that's a thing. It's not directly policy relevant, but where we do get to something policy relevant is that kind of under our assumptions. Remember that we talked about earlier, the thing we care about is d mu dp, that is, which answers the question, if we were to pay everyone more, how would the fraction of people joining the marketplace change? What's easy to estimate is delta, which answers the question, if we keep the system in equilibrium and we pay one person more, how much more likely is that person to join the marketplace? And what we have is that d mu dp and delta, under the assumptions of the model I wrote down, are linked. They were the kind of mean field limit governing all these things are linked by the following system. So what do we have here? This is a linear system with delta. This is, we can estimate d mu dp, this we want to know. And there's a lot of other stuff, essentially demand and supply and this omega function. But it turns out these are all things that are realistically you'd already know. Demand, after the day is over, you know what demand was. Similarly, what fraction of workers chose to become active, that again, you can just measure. And omega, the matching function, this we assumed that the platform knew. So now you have this like elasticity of this matching function. This depends on the matching dynamics. So hopefully the platform kind of has an opinion of what this is. And kind of if you know all this stuff, you can estimate delta, then you can recover d mu dp. And that's our first kind of result here. So now this is now we're going somewhere, because kind of once we get d mu dp, then here I'm not gonna bore you with the details, but kind of then you can use calculus to figure out how does the utility function we care about change with changing the payment scheme. And there's nothing more that's difficult that arises there. So this gets us to the point where we can actually deploy an algorithm. And that is, every time period, what we're going to do is we're going to kind of pick our target payment level, deploy micro perturbations around the payment. Then we're going to estimate delta, this marginal response function, by regressing market participation on epsilons. Then we're going to apply all this machinery I just talked about that kind of solves the mean field limit to map from delta to the thing we care about, the utility derivative with respect to p. And then we're going to perform a gradient update. I wrote it in this form. This is really just the gradient update rule, except with an added constraint that you stay inside this interval of acceptable payments. If you remove this interval constraint, then this is just equivalent to standard gradient descent. And so this is an algorithm we're going to use to update our payment schemes. And what one can check first at a very high level is that if you do this, then kind of everything goes through nicely and you get behavior that you'd expect from something that does kind of first order optimization under kind of strong convexity. You get 1/t rates of convergence in large marketplaces. And we have results in the paper also verifying that under reasonable conditions, the utility function we are optimizing are strongly concave. So these results apply. A little more formally, and this should be kind of familiar from the online learning literature. You can you can give two kinds of results here. So remember this kind of so all these results are going to be in we pick a number of time periods, capital T. Say we're going to run this for 100 days, and then we're going to take the marketplace size to infinity for the number of days fixed. The reason we need to do asymptotics in this direction is that typically the marketplace will be much larger than the number of days you're running the algorithm for. And then when you do this, kind of everything concentrates conditionally under the daily state, and the dominant source of noise actually comes from days are different. And if you have a finite number of days, you're going to have some number of rainy days, some number of sunny days, and so forth. So you need to adjust for that noise, and that's why you're kind of limited by this 1/t rate of convergence. So you can have a first result that kind of only
relies on convexity, of the U functions or concavity. And here, so this holds for any sequence of daily states AT. And this shows that kind of pick any fixed payment P, and then there's the sequence PT you learn. If you take the utility shortfall at day T and upweighted by T, then this is a constant order, which kind of corresponds to a 1/T rate of convergence. Or if you add, so this kind of sample path result, or if you kind of, in addition, assume that the day specific states AT are IID, then you can take a weighted average of your PTs along your path, and this converges at rate 1/T. So anyways, this kind of online to batch type result. Anyways, the form of these results shouldn't be surprising to anyone who's worked in online learning. Which is a nice surprise for me was kind of how nicely the kind of general results from that literature just applied directly to this problem, even though they were kind of the structure overall, one might have expected it to be more different. But so anyways, here you get a 1/T rate of convergence. Now, how does this compare to other things one might do? And here, remember, I showed you a simulation earlier on where you had our method that essentially got 0 excess regret on a scale of the plot. And then you had another method that every day tried a different target payment PT and just kind of updated PT over time. And that thing got horrible regret. And you might have said, like, look, surely you're doing something wrong. It can't be that bad. But actually it is. So you can think of, in the case where you every day you just deploy a specific target payment PT, you can think of this as an instance of the problem where there's some expected utility, U of PT, and every day what you observe, if you deploy PT, and then you observe U of PT plus noise, and the noise comes from maybe it was a sunny day or a rainy day. Actually, this noise has a lot of structure, but here kind of one can simplify the problem and just say the noise is, say, has the same distribution every day. That would only make the problem easier. And now in this setting, suppose you wanted to control regret, that is kind of the cumulative utility shortfall from deploying PT as opposed to P star, that is just the maximizer of this U function. And there's this paper, there's a lot of literature on this. It's a paper by Shamir that shows that the optimal rate of convergence in this problem is like 1/square root of T. I should say that the optimal regret here is square root of T. And this is even if we know that U of P is quadratic, whereas we were getting 1/T rates of convergence. And you might think this is surprising, but actually the problem is just, let's say your reward function is quadratic, so it's a parabola. So what you want to do is you want to learn that the top of the parabola is here, and then you just want to deploy the top of the parabola from here on out. Well, how would you get there? You have two choices. You can sample on the sides. This teaches you a lot about the shape of the parabola, but you pay a lot of regret for sampling here because you're very far from the optimum. Then once you kind of figure out that the optimum is near here, then in this zone, sure, you can sample here without paying much regret. But actually, when you're here, your utility function your response function is flat. So it's very hard to learn about you. So kind of you don't pay much regret, but you don't learn anything either. And there's kind of no action you can take that both teaches you something useful and lets you sample near the optimum. And actually kind of the way you get to square root T regret is you kind of, for the first square root T time periods, you sample everywhere. That'll get you to within kind of 4th root T of the optimum. And then for the remaining time steps, you just deploy that thing. And that gives you square root T regret. And that is actually what we implemented in the baseline for the global experimentation. So there's kind of our method kind of by spiking the system with some micro perturbations and using that randomization, kind of solving that to the mean field limit, we essentially got a gradient of the utility function. And having a gradient in this kind of problem just buys you a lot in terms of rate of convergence relative to zeroth order learning. I should also comment here, some people ask, isn't what you're doing a batched bandit, where kind of you have a batch where you randomly push everyone's payments up or down? And superficially, it looks like a batch bandit. But again, the difference between the batch bandit literature and this is interference, where kind of in every day, if you pay one person more, it doesn't just affect that person, it affects everyone else. Whereas that's not a structure that's usually present in analyses of batch bandits. So the kind of the equilibrium modeling is really fundamental here. Another thing I wanted to just say quickly is there's this paper by Ducci et al., where what they say is that, look, the way you get around these 1/√t rate of convergence problems for zeroth order learning is if you're trying to learn and you have kind of a sequence of functions where you want to kind of find the optimum of the expected function, don't just sample each function once, sample each function twice. And then you can get good rates of convergence again. And of course, what they do is they sample each function twice, a little bit apart from each other, and then update the system by gradient descent. And this is great, except in most applications, how do you sample a function twice? Like, how do you pick a marketplace on a given day in a given situation and both deploy your platform where everyone's paid $15 and ones where everyone's paid $16? Like, you can't do that. So essentially here, by deploying these micro perturbations, we get something that's comparable to sampling each marketplace twice without actually having to do so. Okay, I think I'm pretty much running out of time. Just the last thing I wanted to say is, can we generalize this, and kind of where do you go from here? And this is kind of going back to the beginning of the talk. What's the biggest assumption I made? I think it's this one, which says that workers respond to expected revenue. That is, a kind of workers consider how much you're paying them, market level congestion. They multiply these two numbers, and then that's what they use for making a decision. This bothers a lot. The question is, can we do anything if this assumption fails? And the thing is, essentially, if this function f can depend arbitrarily on p and q, then it's much harder, and I don't know what to do. But there's an interesting in-between case, which is this: if this kind of activation function f depends on a generic bivariate function theta of p and q, that's known. So for example, it could capture risk aversion. I won't go into it now, but you could kind of use this formalism to also capture something like surge pricing. And if this function theta is known, so before theta was just product, but it could be something else, then kind of everything I've said so far goes through. So you can again write down this kind of balance condition. You can define micro perturbations, define the marginal response function, and then you can kind of run similar calculations on the mean field limit and kind of find this kind of system that you can use to solve the QMU-DP. I should emphasize that in this general case, we haven't done everything formally yet. So we haven't kind of, these are just conjectures, but kind of if you conjecture that the similar kind of convergence to a mean field limit would hold, as held in the case I talked earlier, then that mean field limit would satisfy this linear condition that would identify the QMU-DP. So it seems like a lot more can be said. And of course, I think more broadly, a question we've been talking about is that here we were focused on this pretty specific model of kind of
freelance demand, just to kind of have something concrete to think about and be able to kind of have intuitions for whether assumptions we're making are reasonable or not. But I think something we want to figure out now is kind of what is the most general object. Probably this is kind of be a multi-sided marketplace, kind of with supply and demand, both kind of endogenous and kind of more complicated equilibrium going on there. And kind of what is the kind of most general setting in which this kind of argument goes through. That is, you have some mechanism run by a platform. There are some parameters. You want to optimize those parameters that shape the mechanism. And you have kind of these parameters govern the behavior of a bunch of different types of agents. And when can you kind of combine microperturbations with mean field modeling to learn gradients of things you care about, and then be able to update the system that way. But anyways, just to wrap up. So the problem I talked about today, it's one problem with interference. That is the problem where you want to run an experiment, but if you intervene on one person, you pay one person more. That's going to affect others too, because if the one person gets paid more, they're more likely to work, which is more likely to consume demand, which is a shared resource, and that leaves less demand for the others. And then the main result is that in this case, you can use mean field modeling to account for the interference and kind of recover reasonable methods for experimental design with kind of good sample complexity across days. The approach here is very different from kind of the standard way of doing causal inference under interference, where here we kind of try to model the interference mechanism with everyone interfering with everyone, whereas the typical approach is to model interference structure, where kind of only a sparse set of people interfere with everyone, but then without modeling why or how this interference occurs. And at least just for me, something I got out of this is sometimes when you go to, say, a causal inference conference, there's like a lot of work for kind of causal inference without interference under this ubiquitous assumption that you intervene on one person, you only affect that person and no one else. And then there's like one room which is like interference, and this is kind of, you don't make this assumption. But I guess in the space of problems, right, the way to think about it is maybe there are all kinds of causal inference problems, and in most of them there is interference, and there could be interference moderated by a graph, and there could be interference moderated by an equilibrium game, and so forth and so forth. And here in the corner, there's the kind of special case of interference corresponding to no interference, but that's where like 95% of the work in the field is. So at least something I got out of this, that there seem to be a lot of open questions in this area. And I should emphasize, there is a lot of work in interference in the statistics literature. And in this talk, I just had that one slide up front, kind of setting hedges and Halloran and everything related. The reason I didn't talk about it that much is because just formally this approach went in a very different direction. But I think there are many kind of interesting connections there also. Anyways, that's all I had for now. Thanks a lot, and I look forward to having a conversation with all of you online kind of throughout the workshop, and I hope in person again also soon, once the world is kind of back to normal again.